In today's lesson, we are going to look at factors that affect reaction rates, or factors that affect how fast a reaction occurs. The factors we're going to look at are the concentration of the reactants, the pressure of gaseous reactants, the surface area of a solid reactant, the temperature, and the presence of a catalyst. These 5 factors are all factors that we can manipulate in a lab setting to affect the reaction rate. We're also going to look at the nature of the reactants. This is the inherent chemical makeup of the reactants that explains how fast a reaction rate occurs. We cannot physically manipulate the nature of the reactants, but we can use it to explain reaction rates. Let us first look at the concentration of reactants. An increase in the concentration of one or more of the reactants will increase the reaction rate, as long as the reactant is in the rate determining step, which we'll look at in a later lesson. Note that an increase in the concentration of the reactants will increase the reaction rate. Changing the concentration of the products will do nothing to the reaction rate since the products have already occurred. Explaining this using the collision theory will give full marks on a test question. For instance, if you're asked about the effect of the concentration of the reactants, this is what I would be looking for in a test situation. When the concentration is increased, there are more particles in a given amount of space. The more particles in the same space, the better the chance of successful collisions between the particles. And therefore, the higher the chance of collisions with the proper orientation and sufficient energy as stated in the collision theory. Giving more collisions per unit of time, this will increase the reaction rate. In an example between hydrochloric acid and zinc, 2 grams of zinc will react a lot faster in 6 molar hydrochloric acid than it will in 2 molar hydrochloric acid. An increase in pressure will also increase the reaction rate. You can increase the pressure by decreasing the volume of the reaction vessel, which is shown in the diagram. In the diagram, you'll notice that the volume or the space available for the particles have been significantly decreased. It's very similar to how some people feel very anxious or pressured when there's a lot of people inside of an elevator or a very small space. Explaining using the collision theory, as pressure is increased by decreasing the volume, the same number of reactant particles are confined to a smaller space. When the same number of particles are in a smaller space, you're going to have more collisions. Not only will you have more collisions, you'll have more collisions with the proper orientation and sufficient energy, so the reaction rate will increase. There's a much higher probability that particles are going to collide in this amount of space versus that amount of space. The next factor we're going to look at is surface area. Note that surface area will only work for solid reactants, as liquids and gases do not have surface area. Very similar to the last factor of pressure. Pressure will only work for gases. When a solid participates in a chemical reaction, the collision can only occur at the surface, like in this diagram here. The green particles can only be attacked on the outside. If you were to increase the amount of exposed matter, or increase the surface area, for example, then there's going to be a lot more solid particles that can be attacked by another reactant, like in the second diagram. So increasing the surface area will increase the reaction rate. By breaking apart the solid reactant, the surface area is increased and more particles are exposed. We're not increasing the number of particles like in concentration, we're just exposing more of them. More exposed particles increases the chance of collisions that will have the proper orientation and sufficient energy, so the reaction rate will increase. This is why many solids are powdered using a mortar and pestle before being used in a reaction. The next factor is temperature. In general, as temperature increases, the reaction rate will increase. For instance, if you're going to boil a pot of water on the stove and you're getting impatient waiting for it to boil, more than likely you'll turn up the temperature on the stove. Temperature can be explained using what we call the dual effect, meaning an increase in temperature causes two things to happen to increase the reaction rate. And when talking about temperature, you're expected to mention both effects. As temperature of the reactants increases, the particles will have greater kinetic energy, so they're moving faster. Faster moving particles will collide more frequently and with greater intensity, the dual effect. Think of people who are in the gymnasium and they are running around blindfolded. You are going to bump into somebody else more frequently when you're running around, and it's going to hurt. That's the dual effect. If particles are moving more frequently and they're colliding more frequently and with greater intensity, you're going to have more successful collisions. Those successful collisions will have the sufficient energy and proper orientation required, and the reaction rate will increase. When looking at the nature of the reactants, this is the inherent chemical and physical makeup of the reactants, and it explains how successfully they can react. Unlike the past factors, this is not something that we can alter. We can change the concentration, we can change the temperature, we can increase surface area, and we can change the pressure, but we cannot change the physical and chemical properties of the reactants. We can simply use those properties to explain why one reaction will be faster than another. The first nature of reactant that we're going to look at will be the state of matter. Is it a solid, a liquid, a gas, or an aqueous solution? The general rule is that gases, which possesses the most kinetic energy, will react faster than aqueous solutions, liquids, or solids. The only exception to this rule is if we have a simple aqueous ion. They react instantaneously. So for example, if we were to look at these two reactions, you'll notice that the reaction or the combustion of methane will go a lot faster, seeing as methane is in gas form and C23H52 is in solid form. Since CH4 is in gas form, it will go a lot faster. Next, we'll look at the bond type. Reactions involving ionic species will proceed faster than reactions involving molecular compounds. For example, if we're going to look at the reaction of carbon monoxide and oxygen, which are molecular compounds, with the reaction between iron, permanganate, and hydrogen ion, you'll notice that the ionic compounds will react faster than that of the molecular. This is because ionic particles dissolve and automatically separate into solution, so the individual particles have no bonds to be broken during the collision. They're already broken as soon as they were dissolved in water. Molecular compounds have covalent bonds, however, that must first be broken before the molecular compounds can react. This takes a lot more time. Bond strength. Reactions involving breaking weaker bonds are faster than those that involve breaking stronger bonds. What that usually means is that reactions involving a single bond will react faster than reactions with a double bond or a triple bond. Less collisions are needed to break the weaker bonds than stronger bonds. Reactions involving the breaking of fewer bonds per reactant will also proceed faster than those involving breaking larger number of bonds. For example, if we were to just look at two different combustion reactions, the only difference here is our hydrocarbon, C5H12 versus C10H22. Well, in the reaction involving 5 carbons and 12 hydrogens, that will be a lot faster than a combustion reaction involving 10 carbons and 22 hydrogens. So the fewer bonds that need to be broken, the faster the reaction. When looking at acids, strong acids are completely ionized in solution, so they will react faster than a weak acid, which is only partially ionized. There are 6 strong acids that you'll recall from prior chemistry courses, and those 6 strong acids will react faster than any other acid. So if we were to look at the example between hydrochloric acid reacting with zinc and acetic acid reacting with zinc, we have a strong acid in hydrochloric acid and a weak acid in acetic acid. Since a strong acid completely ionizes and is already broken apart for us, it will react a lot faster with zinc. Metals with low electronegativity will react faster than metals with a higher electronegativity. And recall that you'll find the electronegativities on your periodic table. This is because the lower the electronegativity, the more easily a metal will give up its electrons. The more easily it gives up its electrons, the faster it will react. If you were to look at the reaction between lithium and potassium, you'll notice that they're both reacting with water, so we can compare the two reactions. Lithium has an electronegativity of 1, where potassium has an electronegativity of 0.8. Since potassium has a lower electronegativity, potassium will react faster. The last factor we're going to look at is a catalyst, and a catalyst is just the sixth factor, not part of the nature of reactants. A catalyst defined is a substance that you can add to a reaction that will speed up the reaction rate without actually being consumed in the process. It provides a new pathway or a new reaction mechanism to form products, one that requires less energy. Therefore, if you were to add a catalyst to a reaction, it will speed it up by lowering the activation energy for the reaction. Therefore, more particles will have that required energy to overcome the activation energy barrier to form products. You'll notice in the potential energy diagram given that we have the original potential energy diagram, a very high activation energy, and this is probably a slow reaction. Once we added a catalyst to the reaction, however, the catalyst lowered the activation energy. Sometimes it lowers it in 2 steps, as seen here by 2 bumps. Sometimes it will lower it in only 1 step. Just all depends on the actual catalyst, but essentially it's just something that you add to a reaction that will speed the reaction up by lowering the activation energy. There are 2 different types of catalysts. There's a homogeneous catalyst, which exists in the same phase as the reactants. And then there's a heterogeneous catalyst, and that's a catalyst that exists in a different phase or a different state of matter than the reactants that it catalyzes. This brings us to the end of our study on factors that affect reaction rates. Please familiarize yourself with these 6 factors and be able to answer questions on them based on the collision theory.